Okay, thank you very much. And thanks, Christy, for the introduction. And can I just hide my own? Okay. So again, my name is Jian. I'm an assistant professor at the Department of Visualization, which will be moved to the new School of Performance, Visualization, and Fine Arts. And I'm also assistant director for project development at Texas A&M Institute of Data Science. So today I'll be talking about cloud computing and big data analytics using cloud computing resources. So I gave a similar short course at high performance research computing here at Texas A&M. The goal there back then was to introduce PySpark and big data analytics on top of our big systems. I mean supercomputers. And I'll probably I reserve one slide just talk a bit more about HPLC and all the computing resources that you might have access to at Texas A&M if you are affiliated with A&M here. So the organization of this talk, this presentation could be divided into 4 parts. We'll have a 10 minutes break in between after about 1 hour. So part 1 will be a short introduction to cloud computing. And we'll go through some basics of the all the fundamentals of cloud computing, and then I'll introduce PySpark, which is one of the most popular software module developed for big data analytics. And the Spark itself has multiple language bindings, and Python is one of the most popular language used in the data science community. So I cover mostly about PySpark. And for those of you who are familiar with R and some other languages, you can look into other documentations, and I provide the links to those resources. But fundamentally, it's just Spark, which is the same infrastructure used for different user communities. But here, PySpark is the one we'll be focusing today. And then we'll talk about some details about PySpark, especially the RDD, and we'll go into detail about that. We don't need to worry about it at this point. And we'll discuss a bit more about DataFrames used in PySpark, and which is building blocks for all the other applications based on PySpark software stack. And then lastly, we'll cover some simple data analysis with PySpark with some examples. There will be some online hands-on sessions available if you want to try out. I can open up the GP notebooks on Google Calendar and go through some of those, and then I'll leave you all just to work on those yourselves. And we should have sufficient time today to answer some technical questions. If you have any, feel free to let me know, and I'll help. I'll try to see, if I can help you. Sometimes it could be too complicated for me to even answer those questions because it's just so big area of research and development. So let's get started by introducing cloud computing. I consider myself as a user. I'm not a researcher on cloud computing itself, even though I did some work with collaborators from Japan on containerization technologies using Docker and trying to figure out better ways to do a file synchronization, etc. But so this talk, this seminar is mostly about using cloud computing resources, not much about the research side. So, so this is more from perspective of a user. As a user, I have multiple devices myself. I have phones, I have iPads, I have my laptop, I have my servers running both at my home and also in my offices. I have desktop as well. So I have all the devices that are showing on this slide. And no matter I want or not, all of those resources are connecting to the cloud computing platform nowadays, either through Google Cloud, Google Calendar that we'll be using today, or to Microsoft Azure. Even you don't know that because a lot of online services are provided based on Microsoft Azure. If you are using Amazon to do anything, you might be using the Amazon cloud systems anyway. And those are so-called infrastructure platforms provided by those big companies. And they are providing applications on top of that, such as, say, Google Doc. You have even your Alexa, your assistant, you're based on the cloud services, all the applications. Netflix is using cloud computing applications and resources to stream their videos and other materials. And you have many other things. So cloud computing is much more than storage nowadays, even though a lot of users got started with cloud computing platforms by using their cloud storage systems. But as you will see more and more in this, several slides in the future, in this talk, we are using not just storage, we're using computing powers, we're using memory, we're using accelerators like GPUs, TPUs for computation. And sometimes you know it, sometimes you don't know it. So that's exactly what's the purpose of cloud computing. Basically, it's trying to provide some on-demand computing resources and with our users to actively managing those resources. So part of the first part of this seminar is trying to explain and try to demystify the magic of cloud computing. So it's not magic at all. If you look into the implementations and all the software modules and hardware infrastructure, you can see it's accumulated work of decades of hard work by computer scientists, all the researchers, and all the people working hard in companies. And it's not just one person's effort. It's accumulated efforts by probably, you can say, 1 or 2 generations of researchers and computer scientists. And it's a lot of work. And fortunately, we are now, able to use those resources and do something more interesting, mostly on research and science related subjects. So this is, I would say, biased because this is the history I think is probably more important from my own perspective as a user. If you go to IBM's online white papers about cloud computing history, they have different timelines. And if you go to Google's and Amazon, they have their own timeline. But I think I covered some key milestones, in the history of cloud computing at its here. But again, feel free to feel, to look into the history yourself. And there are many online articles about that. People are still arguing about who first came up with this cloud computing term. But again, that's not important. The important thing is that it's there, it's everywhere, everyone's using it. And it's still rapidly developing. And I was starting with 1960s, when Jian McCarthy and MIT first suggested the sending computing power as a utility, just like power grid. When you plug in your electronics into the power grid, you use the power, you pay the bill, and someone measures the utility, and that's how you use electricity. And the same idea could be applied to computing power. But back then, of course, there was no such thing like cloud computing, or even grid computing, or any computing, shared computing like that back then. So computers were designed for a very limited amount of users for military and other things, which are crucial at that point in time. In 70s, people started to talk about virtual machines, which actually are a key concept in cloud computing. Now, given the cloud computer, the first thing you do after you get a cloud computing platform, you'll be creating some virtual resources, either as a virtual machine or like virtual server or virtual services. And the key idea about cloud computing built upon the concept of virtual machines. And we can talk about that a bit more because it's very important for cloud computing. And then in 90s, there have been a lot of work on virtualization. The idea is to have the same set of hardware. It doesn't really matter if you are running Linux, Unix, Windows, Mac, etc. As long as you have the same low-level APIs, that's people building those operating systems could directly rely on. You don't need to worry about which operating systems you're running. You just need to install your operating system on top of the virtualization layer, which is usually called a hypervisor, or sometimes VMware was one of the very famous virtualization company trying to provide this interface between hardware and software. So then you can virtualize different operating systems, and all the operating systems will be sitting on top of the same architecture. So later on, you probably heard about grid computing, which was, I mean, it is still, we are still using it, but in a small community, not small. I think it's still widely used for transferring files between different computing centers in academia. And but the major concept has been taken over by cloud computing now. That's mainly because it's kind of similar. The idea for grid computing is to provide a computing grid similar to power grid that you can plug in and do something. But grid computing was first adopted mainly by high-performance computing community. And there have been a lot of work trying to figure out a better way to share the resources among big computing centers. Like Tamu here, we have a supercomputing facility back then many years ago, and to share the resources and among universities and institutes, that's a big concern back then, and it still is. And now there is other technologies, and we can talk about that later. In 2000, a lot of commercial cloud computing services popped up, especially AWS, Amazon Web Services, and also it provided so-called elastic compute cloud that users can directly get onto their portal and reserve some virtual machines on their cloud computing system based on your needs, and make it really elastic in the sense you can easily scale up to the number of servers and nodes you need for your applications. And this is extremely useful for small business when they are going to expand their business and they don't want to pay the upfront cost to expand their space and buy new servers. You can directly say, hey, I want 1,000 servers instead of 100. And cloud computing can do that instantaneously as long as the resource is available. So it's a game-changing scenario for small businesses. That's why you see a lot of startups getting up. They don't have any resources themselves, computing resources themselves. They're just renting the resources from cloud computing service providers. Similarly, you have Google, Microsoft, you have Azure, Google Cloud Computing Platform, etc. And then there is another big milestone. It's called Containerization Technology. That's something I worked on myself. So the idea is that instead of using virtual machines, which requires pretty big image to start your virtual machine on top of the cloud computing platform, you use a container, which is like a lightweight virtual machine. And all the containers will be relying on, as long as the containers are using the same operating system, all the containers could be just simply rely on the same layer of virtual environment. That the time taken to start a containerized application will be much, much faster than starting the whole thing from a virtual image that you uploaded to cloud computing system or deploy it. So containers can quickly start it and shut down, and it's just dramatically changes the way how the cloud computing services are provided by all the service products, especially Amazon, Google, and Microsoft. And that will actually change the way how they're charging users and make it much, much cheaper to use, for regular users to kickstart something, small and try to run something quickly. So in 2020s, cloud is almost everywhere. We are using that, as I just mentioned at the very beginning. Even if we don't know it, we're probably using it. It's just everywhere. It's getting ubiquitous, and it's especially helpful for researchers doing a lot of other things. As far as the deployment of cloud computing is concerned, there are basically three kind of. At the bottom here, I have. I'm not sure if I can draw something with my pen. Okay, it's probably not working here. So at the bottom here, it's, I show the one on-premises systems. These are just traditional regular servers you're hosting by your own, hosted by a smaller group or a smaller unit or by just a single team. And it's mostly just ordered privately. You don't connect to the public cloud or even other cloud facilities for sharing any resources, just your own server. That's a traditional way of using machines, which is still common today nowadays, but now more and more users are trying to connect to the cloud. You can directly connect to the public cloud, and I'll show you some examples today with with Microsoft Azure. And you can directly connect to your private cloud, which could be set up and created and managed by a local group. Here at Texas A&M, we do have an Anki cloud. I would call it a private cloud because it's hidden from the public cloud by a firewall. But as long as you get things worked out, you can get it connected to the public cloud, if it's needed. There's also a possibility to create a hybrid cloud that you can share part of the resources, from the public cloud, and your private cloud can get connected to some public resources for backing up and synchronization, some files, etc. So it seems to be more and more practical now with a hybrid cloud setup, and it's getting really popular nowadays, mainly because it's just cheaper relatively compared to hosting your own on-premise computing servers. And also it gives you extra redundancy for backing up your data with much less cost. So we'll talk a little bit about this in the next several slides, mainly because for NM and for your own public cloud usage, you might need to look into your requirements to figure out the better accumulation and give you the best return of your investment. So for the service models, for the on-premises, as I mentioned, everything is managed by yourself. You need to either do it yourself or hire someone to do it for you to manage both hardware and software. Keep all the security patches up to date and make sure your application runs, make sure all the versions, whenever there's an update, your application is not broken. And all this is just a big headache for smaller research groups. So that's why cloud computing is really, really helpful for groups that who are not that technical savvy. And there's another, going from the left to right on this diagram, you have IaaS, which means it's infrastructure as a service. So Google, Amazon, and Baidu in China, Tencent, Alibaba, and Microsoft, all these companies are providing IaaS at least. So they're providing all the hardware servers. They build up huge data centers. Microsoft even built one underwater. Probably you read some news about it. And they have been testing on different ways to build all those huge centers to just because of massive deployment that can greatly reduce the cost for individual servers. So they are trying to build as big as possible, build all those data centers as big as possible. But again, the power consumption is a big concern. So that's why usually you probably need to build a power plant right next to it, for you to generate power to prepare for any emergency and other things. And also cooling is another concern. That's why a lot of data centers nowadays are built near rivers and near lakes, etc. So on top of this infrastructure, users can install their own operating systems and then their applications deployed on those. And go even to the right here, we have a PaaS, which is a platform as a service. And now the service providers were not only providing the hardware, but also software. On top of that, you have some middleware and a runtime. The users only need to worry about particular application need to run on those, and the data needed to be synchronized to those servers. And then the last one, which I think is current one, is used a lot by us using phones and tablets. We are using so-called application based, or it's a software and the service deployment service model. And we are simply using Netflix, Google Doc, Google Drive, all those as an application. We are not deploying anything about the runtime, any software. As long as we install it on our client side, everything's ready for us. So that's the software and the service. This is mostly targeting, the final users. When you have a mass public that can get access to the resources provided by the service. So pros and cons of cloud computing. Again, I'm probably a little bit biased here because I think because cloud computing is getting really useful and popular, I think the cons definitely will be less than pros. And that's why, everyone is using cloud computing resources and platforms. But again, let's get to the bad news first. So for cloud computing, you probably want to consider some security and privacy issues, mainly because no matter how trustworthy those cloud computing platform providers are, and you are giving your data and your resources, your data mostly, your data and applications to a third party. And there might be security concerns no matter what, even if they are very, very safe compared to your own server, but again, it's other people's hands, right? You always have the risk over there. And also for all the online data, which will be accessible online anyway, otherwise you wouldn't be able to access it yourself. And for all the data that posted to the cloud computing platforms, they are subject to attacks, and there are a lot of cybersecurity issues concerned about those. Probably it's safer just if you save the data to some servers that are completely physically detached from the internet, if you are concerned about cybersecurity. But again, it's depending on the level of security and other privacy concerns you have. And this could be a cons, but many users, if they control the data themselves, they're probably not adopt those very secure measures compared to those online cloud computing providers. So this might not be a con for cloud computing, it might be a bonus for them because it's just the extra measures they took with regarding to security and privacy. Another cons is a control and flexibility. If you give your data and things to other people, you won't be able to get it right away. It's not like in your phone or in your USB drive, you can directly download it and use it right away whenever you need it. Then you'll be relying on the network bandwidth conditions and also even the availability of the remote data center. Sometimes they have a downtime. It's not 100% on time. And that's the control and flexibility with regarding to the cloud computing platforms. For pros, it's pretty easy for me to say all the good things about cloud computing, mainly because it's just so dramatically changing the way how the computing resources are shared and used. The very first thing is no upfront cost. It's the biggest bonus for many users. You don't need to buy any hardware yourself. It's like renting and buying kind of scenario for real estate, right? You, depending on your scenario, depending on your needs, you might want to buy a house instead of renting a house, or buy a car instead of renting a car. Similar idea applied here. Of course, if you calculate the total cost, you might pay more for particular applications if you want to download data and share the data a lot, because every time you download data from some cloud storage systems, you need to pay a fee for the total data you downloaded. Even if it's your own data, but you'll pay for the bandwidth. So, there is a small charge for that for long-term backup. But again, you needed to do the math and figure out the better way to do that. But it's your problem to figure out. It's not their cloud computing platform provider's problem. And then the time to solution is very fast. If you already know that you want to use a very specific services, and you can just directly get it and run it, and it just takes minutes, sometimes seconds to get started. And then scalability is a big bonus for cloud computing. If you want to go from 1 user to 100 users, or if you want your company is scaling from 1 customer to 1,000 customers, or even 1 million customers, you can do it with cloud computing systems. just imagine if you just running everything on your own server, how much overhead it will be for you to scale up your server room and scale up your computing infrastructure. And reliability is it's actually highly dependent on the vendors. Some vendors that do have extra guarantee about availability. About sometimes they can reach to 99.9% or percent of uptime, depending on which vendor you are using. And sometimes they have, in most cases, they have a redundancy, basically they back up all their stored files, mainly because storage is getting cheaper and cheaper, and the premium to pay to buy the extra hardware to increase the redundancies is getting lower and lower. So they do have the resources to give you a pretty high confidence about, they're pretty confident about backing up your file and give your something assurance about the reliability. That's another bonus for cloud computing platforms. So there are multiple commercial cloud computing platforms that are operating here in US, and there are also some Chinese, and I believe there might be one or two European cloud computing platforms, but they are not very big. The biggest one are Amazon, of course. It's 33%, 1/3 of the total market share, and Microsoft Azure is the second one. As far as this survey is concerned, I don't know how accurate this survey is, but it seems to be the one cited by many users, many people. So I assume it's the numbers are good here. So Microsoft is about 1/5 of the total share, and then Google and Alibaba, IBM, etc. So these are the commercially available cloud computing platforms you can use. You pay the fee, you use it, just like pay as you go. You just pay whatever you need. It's a very decent scenario for many users, that you don't need to pay the full price for the servers and maintain it, years after years to use those, even though probably you don't want to use. Probably the computing resource got just wasted during the time if there's a lot of usage on those. So another one, which is an alternative that I mentioned previously, is that the high-performance computing resources available for AM users. Actually, one of the resources here, which is not listed, it's called Faster, another one is called Access. So both of them are funded by National Science Foundation. So technically, you are supposed to be providing certain computing hours or storage and all the stuff to users across US. So all the other institutes should have access to some of the resources available. But these three are the ones dedicated to AM users. If you have a net ID, and even if you don't have a net ID, you can collaborate with your collaborators here at AM to get free computing hours to run on those big machines. Again, these are very, very decent systems. Just look at the very left one, Grace, which is a new system added to the AM system. It has many, I forgot how many, probably 40 or I forgot how many, 20 GPU nodes. Those are 40 gig GPU nodes. It's just specially designed for training machine learning models and for deep learning neural network training models, etc. So those are very good for compute intensive applications. And again, if you look at the global disk, it's huge. It has just Grace itself has about 9 petabytes. 1 petabyte is 1,000 terabytes. Just look at the storage we have. Those are free, and those are bought with the taxpayers' money, and it should be shared by researchers anyway. So don't just, before you get started to buy some computing hours on those cloud computing platforms, just get started with this system first. The way how I use them, even though it's kind of different interface, if you're familiar with Windows or Mac, all of them are actually Grace and Terras are Linux-based. Vido, actually, it's like a cloud computing platform. You can start your own Windows interface. And if you want more information about it, you can go to HPRC website, and I have a link here at the bottom. So there's another service provided by an IT department, IT division, and this is called an Angie Innovation Platform. They provide links and the resources to Angie Cloud, which is a private cloud I mentioned previously. And it also has links and also some master contract with AWS, Amazon, Google, and Microsoft. And there's another one, I think, Star. I'm not familiar with that for myself, but I'm a user for the Angie Cloud, and I do have a web server running over there for a project. And it's just working like many other commercial cloud computing platforms. And it's just similar interface, and I'll show you how that works in a second. So if you are going to get started on cloud computing, if HPI systems are not working for you, you can go there, go to AIP, and it's called the Angie Innovation Platform Concerted. Or you can just type in cloud.tamu.edu, and you can get in there. They're very simple to get started. There is no extra overhead cost. You are directly paying what you need. And also, there's a campus subdomain you can create, and you can get the domain name and point to the server you are hosting. And this one also has identity management for all the AM users. So this is a simple example I want to show about Microsoft Azure. I use the Google Cloud platform myself. I use AWS, but Google Azure seems to be, this one seems to provide a very, very intuitive interface compared to others. Like, I'll just show you one here, but others are similar, but this one seems to be easier to get started if you are brand new to cloud computing. I think I can zoom in a little bit more here. So when you get there, you log in, create an account, and actually AM has access, master contract with AWS. Your net ID could work there. As you can see to the top right, I do log in with my AM email address, and then it's under the domain of Texas AM University. And you can start by creating a resource here. And after you click that, you'll get to another page, which is pointing you to all the other things you can do. You can create a SQL database, you can create Azure database, you can create some other online services, but the most commonly used is to create a virtual machine yourself, which will be just like a machine running remotely that you can have access to and do other things. And then after you collect this virtual machine, this will pop up, and you need to look into all the configuration you need. And depending on where you are, you want to pick the right region, because all the cloud community services, they have distributed all the servers in different regions, so that they have less networking congestions. If you have one server sitting somewhere, people from outside might have trouble with the networking. So they have distributed servers serving different regions in the US. You can pick one, and also at the bottom here, you can see it's not cheap. If you want to rent, say, standard 2 virtual CPUs with 8 gig, I'm sorry. So with 8 gigabytes of memories, 8 gigabyte memory, and you'll need to pay like $72 per month, which is not that bad. Consider you can use this system for as long as you want, and consider buying a computer for 5 years. That's about probably cheaper, but again, this will give you the freedom to just shut it down and just stop the service and try something else yourself. And then this one shows you all the options you have. You have smaller one, bigger ones. You can even add GPUs, and there are many other things you can do. For the IOP here, the max IOP here is mostly about the disk operation, like disk performance. How fast you want to, how fast you want the disk to be. Sometimes if you're in SSD, solid state disk, you definitely get much faster, and the traditional ones getting slower. And because it's shared by multiple users, you can get even slower disk performance. But again, you're paying what you get. So paying for what you get. So it's, if you're getting cheaper, then definitely it doesn't perform well, but it's getting, if you want high performance virtual nodes, you need to pay a premium for them. So lastly, you can go to the Microsoft Azure portal, and there is a quick start center. and get you started quickly. If you don't know all the details, it's fine, get there, and it will get you started. So I think that, it has been decades for all these companies to work on this. This is probably, more than 10 years. It's not multiple decades, but more than 10 years for them to correct all these user interfaces. They have been considering beginning users, have been considering advanced users. So they have spent a lot of time to get things working nicely with this nice interface. So I assume if you just want to get started, get to one of these commercial cloud computing platforms that try things out. It's just very simple, and they usually offer free credits for you to get started. You don't need to pay a hefty fee to get started yourself. So let's jump into the part 2 of the introduction to PySpark, and we'll take a short break, and I'll answer questions after that. I know you might have some questions about cloud computing, and we'll answer them during the break. Probably we'll have about 10 minutes break. So PySpark is one of the most popular big data analytic frameworks, and you can consider it a successor of the Hadoop framework, which was used and it's still used, but it's not as popular as the PySpark nowadays. Hadoop was used a lot for, probably I would say 10 years ago, for people doing file-based data analysis, and they needed to store the file into files, and the file will be distributed among multiple nodes, different processes on the cloud computing systems, and all the files after they got analyzed, the output will be separated into files and then getting back to users. And the PySpark is dramatically different in the way of organizing all this data. PySpark is based on memory, so everything is written in memory. That's why it's much faster than Hadoop. But again, because memory size always much smaller than storage size, like disk size, so you cannot deal with extremely large data sets compared to Hadoop. Hadoop size is just the size of data you can analyze with Hadoop is limited by your hardware storage, but PySpark is more or less limited by the memory you have. But again, there are many techniques to combine Hadoop and PySpark, so you can do some of part of your data analytics using Hadoop and part of that using PySpark. But today we'll be focusing on PySpark here, but I'll give you a very short introduction about Hadoop as well. So PySpark is a Python API. API means Application Programming Interface for Apache Spark. Spark was started a while back at University of California, Berkeley's MP lab. And later on, the code base was donated to Apache Software Foundation. And it's one of the flagship software at the Apache Software Foundation. And the whole purpose of the goal of the Spark, the reason why Spark was created, is to make it a general purpose cluster computing framework for real-time processing. So the real-time processing here is the key here, mainly because it's memory-based, it's really fast, and it's pretty efficient compared to other big data analytics frameworks. So the Spark itself is written in Scala. It's a programming language kind of similar to Python and Java, I would say, probably most similar to Java, but it's not commonly used, for general programming purpose, even though itself is pretty generic. A lot of things could be written in Scala, but Spark is one of the most popular applications in Scala, and you can look for some other applications written in Scala, but Spark is the most famous one. And mainly because many users we know who are doing data science, analytics, and model building, they're using Python. So that's why this PySpark was born. It was just to provide the wrapper around this Scala-based Spark, so that you can use the Python programming language to program Spark. So here comes a brief history of Spark. I always like to go through the history so that you can know how things got evolved. I think it's good to understand how Spark came into being by looking at this brief history. I started in 2009 at UC Berkeley, and then it's open sourced with a free open source license, BSD license in 2010. And then it was donated to Apache software foundation in 2013, and then the first 1.0 in open source community is always means stable release. The 1.0, if anything between 1.0 is always considered as unstable or not matured or something like that, still feature ending stage, you're not ready for the stable release. So 1.0 it's always considered as, almost always considered as a stable release for any software, open source software. So Spark released version 1 and become Apache's top level project in 2014, and the 2.0 was released in 2016. And the 3.0 was released in 2020, which was pretty close during the pandemic. And the latest version is, actually this one should be updated. I think it should be 3.3 as of so far, July 2022. I needed to update this line. And when I share my slides with you, so I'll update it. So Apache Hadoop is like a competitor and a friend for Spark. They have been working on, they have been targeting similar, or if not identical, similar user bases, but they are doing something dramatically differently, in a dramatically different way. Hadoop is using mostly file-based model. It's trying to write into files, using files for saving, sharing, and anything. And Spark is storing data in each node's memory, and instead of using the hard drives, so that the data will be more, quickly processed and actually, from one perspective, Spark is, is a competitor, but now Spark is getting into the Hadoop ecosystem. So for people doing Hadoop related, data analytics, they use Spark as an extra module to help them to speed things up. So that's why they, it's kind of a friend and a competitor kind of relationship between Spark and Hadoop. But again, for open source users like us, no matter how serious the competition is, we are using them like tools. So it's not a big concern for us. As long whichever is better for your application, you pick whichever. You don't have to be strongly against one, strongly against one or supporting another one. So it's just the tools. For the Hadoop ecosystem, there are so many applications. If you are using the big data analytics community, you probably have already used HDFS, called Hadoop Distributed File System, which is a basis for distributing, managing all the files across multiple nodes, multiple cloud computing resources. And there are also some resource managers like Yarn, yet another resource negotiator, YARN, help you to manage all the files, how they are distributed, and how you want to schedule your computing resources, etc. The MapReduce is one of the biggest things in Hadoop. Probably heard about this already. And it's mostly using programming to help with data processing. And there are many other things. I won't go into details, but just want to show you, this is a big overview picture for the Hadoop ecosystem. Spark is just one component of it. And we'll not go into detail about Hadoop, but just let you know that Hadoop is the superset of what we are doing here with a Spark. If you want to deal with even bigger files and even big data sets, Hadoop might be the only solution you can find, open source solution you find. There might be some other solutions, but Hadoop seems to be the one used by many people and getting really fine-tuned and refined to do the work it's supposed to be doing. For the Spark ecosystem, that's within the Spark ecosystem itself. It's it has multiple language support with Scala, Java, Python, even R. I know a lot of students and researchers here in biomedical area. R is one of the most popular languages used by many researchers, and Spark fortunately provides interface for R as well, so you can directly use R to call Spark functions and do something like what we're doing with Python. It's just the interface will be different, but the functionalities, everything else should be similar because we're all using Spark underneath. It's just an interface a little bit different between R and Python and Java programmers. So there are multiple, modules inside the Spark ecosystem. Spark Core is like an engine providing all the connecting, like a glue, put everything together. And the Spark Streaming is mostly about dealing with the real-time streaming data, which is very important for nowadays, the IoT and other things you might have heard about. And IoT means Internet of Things. And, it's connecting and sharing all the sensor information between your home appliances and all the other sensors you might imagine. And IoT is trying to collect everything together. So the internet in the future will be internet not just for people, also for things, for sensors. And Spark is able to do the streaming for the real-time measurements data. And Spark SQL, it's a SQL interface for Spark, and Spark can use SQL language to do the query and other things, and whatever you learned previously using, MySQL or SQLite or PostgreSQL and Postgres. I'm sorry, I forgot the PostgreSQL, and then everything will be working in a similar way, or sometimes even identical, because the SQL language itself is standard, so you can use that for querying data and do other things. GraphX is a Spark API for graphs and graph-related analytics. Machine learning library is a machine learning library provided by Spark community, but it's not widely used, but it's still something that you can use if you want to build up some machine learning models directly using Spark. And then Spark R is a bunch of R packages that help you to deal with R and R related, use R and R related modules. So I won't go into this one. If you're interested, go into the, you can look into the difference between Hadoop and Spark and see how they're different for different applications, different usage. And there are other things that you want to look into. It's about memory against file-based processing. Speed is a major concern, and also flexibility is another concern. So as far as Spark is concerned, there are 4 or 5 layers. At the very bottom of the storage, you're using Hadoop distributed file system, you use a NoSQL database or SQL database, use a cloud computing storage system just to store your files. You can directly use those as a hardware layer, storing all your files and data. On top of that, you have a cluster management. The reason why cluster management is so important for big data analytics is because for a lot of tasks you're doing with big data analytics, using big data analytics, will take probably more than seconds or minutes to finish, right? Sometimes you take days, weeks, even months, sometimes, depending on how big the data set is, how complicated your algorithm is. So you will need some management system to manage the computing resources. And especially when you are dealing with a shared system, especially when you are on the computing cloud system or a cloud computing system or on a high-performance computing system, you need to talk with the scheduler. The scheduler will schedule your job based on your requirements, also based on the availability of the hardware resources. So you need some management mechanism and to manage your clusters, manage your computing resources. So there are multiple managers here. Hadoop YAR is a very potent one used by Hadoop community. Apache Mesos is used for managing multiple cloud systems, very popular, very powerful. And Spark has this old scheduler. So you need to create a Spark cluster yourself, and then Spark scheduler will manage your Spark cluster. The Spark cluster could be loosely coupled nodes. You can use public cloud, on-premise systems, but you need to tell Spark that this is a cluster I set up and use it. So Spark will look for the nodes available and the computing resources available, and schedule jobs on top of this based on whoever submit first or depending on the availability of the resources. So that's cluster management is a kind of crucial component for big data analytics, mainly because the total computation takes time, and a lot of users are sharing resources for big data analytics that don't have their own dedicated server. Otherwise, you just run it. It doesn't matter. But now with a shared system, you have to deal with management and schedule. So on top of that, at the center of everything is a Spark core that's engine, like a glue to put everything together. So then all these different modules and components can talk to each other. they communicate, they share information, and they schedule all the tasks, you know, together. And it's like how to say, like a framework and a platform to get everything together. So on top of the Spark core, you have libraries, and you can do a SQL query, and you can do streaming, and all the libraries I mentioned previously, they are all working here on top of that. And then at a user level, you can develop your applications using Scala, R, Java, Python, and just call those libraries, and then those libraries will use the Spark, will managing all the resources through Spark core and all the cluster manager, and getting the data analyzed, and then the results outputted or exported. So that's the rough structure. So as from a job, you know, a task and a job related perspective, you can consider the cluster manager is at the center. That's managing all your jobs. After you get your program done, you submit to, you create a Spark context. That's something we'll talk about in a second. You create this, you know, all the, how your analytics program will be running, how the data could be attached to each tasks in your program. And the whole thing will be submitted through the cluster manager to the workers. The workers here, they could be either high-performance computing systems, could be cloud computing systems. And the cluster manager will virtualize every computing core, or your CPU, or even your memory, into smaller computing units. So when you submit a job, you just need to tell cluster manager, say, hey, I want to run my job. Just do your best. You know, if your job is too big, the cluster manager will just reject your job and say, we don't have enough resources, we don't have enough memories, or probably your job is taking too much computing resources. Otherwise, you'll take your job and submit it to the workers, and workers, depending on their availability, they'll take your job. And so the class manager here, more or less like a proxy, you know, managing all the things like agent, you know, taking your job and assign it to workers. And it's how things are working this way. So we have a simple example, and we have about 10 minutes to go through this. And I'll first go through this quickly, and then I'll ask everyone just to click the button here to just try it out, to see if you can get anything running on Google Containerization, which itself is a cloud computing platform. And we are running PySpark on top of that to carry out some computing tasks. So the computer task we are going to do is to calculate pi. This is a very, very interesting way to calculate the value of pi. I'm not sure you ever heard about it. So the basic idea is very, very simple. So given a square and a random number generator, I generate random numbers on this square with XY coordinate, okay? So when you draw the biggest circle around this, inside this square, the biggest circle inside this square, and you can imagine, because the random numbers generated uniformly, we are not doing, you know, Gaussian distribution, just a uniform generated. So every point in this square should get an equal chance of getting this dot generated, get this random number generated, this XY pair. So it's now, because the random number are uniformly generated, the ratio of the point inside this circle against the number of points inside this square should be equal to the area of this circle compared against the square. So if you calculate this the circle, the area of the circle, which is pi r squared, assuming our r is 1, so pi r squared is just pi, and the area of the square is just 2 by 2, because every side has a length of 2, so 2 by 2 is 4. So the ratio of the total number of random numbers inside the circle against the ratio, the number of random points inside the circle divided by number of the random numbers inside the square should be equal to pi over 4. So this turns the calculation of pi into just a counting problem. Just need to count how many points are there in this circle and how many points are there outside this circle, how many points are there in this square. And then you get a ratio and multiply that by 4, you get your value of pi. Okay. this is a very, very famous problem for calculating pi here. There are many other ways, and this is just one, I like it very much, and I use this for teaching parallel programming and other things. It's pretty interesting problem. And also the coding part is very, very easy. And this is a serial version to calculate that. If you're running on your computer, as long as you get a Python console out or your favorite Python IDE out there, just copy paste it and you can run it. And you can see if you have a number of samples here, it's the total number of points you want to random generate it. That's 1,000 here for the small problem. And you can see your pi is kind of like close to 3.14, but not exactly. So you're getting errors. And as you can imagine, if you get more and more samples, you'll get more accurate result. Now, for Spark, this is how we do it. We create a Spark context, and then we define a function to decide if the point is inside or not. And then we use a Spark parallelize function call to run this inside function in parallel. And then finally count how many points are there in parallel, and then we get our pi value calculate. Okay, now you can just click this button. If you click open in Google Cloud, you needed to have a Google account. If you have your Tamu account, should work perfectly. I'm using my Tamu account anyway. So if this is your first time running Google Containerization, you can click on each cell. Every one here, every box here, it's a cell. You can run it with a Shift Enter or Control Enter, or you can directly click the Run button. It says this notebook was not authorized by Google, but it's fine. It's from my GitHub repository. Just feel free, don't worry about it. And I double checked, there's nothing banned there. So you can do that, or another way to do it is to click the menu bar at the top and click Run All. That will run all the cells one by one. So what I'm doing here first is trying to download and install PySpark. Because Google Containerization is every time you start a new session in Google Containerization, it doesn't know anything about PySpark. It installs some other modules and TensorFlow, machine learning models, and others. But PySpark was not one of the default modules installed by Google Containerization. So you need to install that every time you start this. But of course, when you are still running this will be installed. It will be there for you. But after you close this Google Containerization Jupyter Notebook, and you close up this session, when you log in first and log in the second time, you need to install this one more time. But fortunately, this package is not that big. And also, as you can see, the network on the Google Cloud is pretty fast. It's like, when it's try to download this Pi and all the packages, the speed is pretty good. It's the network bandwidth is pretty high. So now it's already run, and let me try to run all. So it's already downloaded, so you can still run the first one, but it won't install anything because it's already installed. Then it will start run the second one. What it's trying to do is create a new Spark session. And this session will open up the port. And this port could be accessible outside. So let's start with a simple serial version. Oh, this is a Spark version already. So we have about 10,000 sample points. If you want to check it out, there's a link. This link will create this is another hack I added to this notebook, is that you can create a channel. And this on Google Containerization. The channel of this Google Containerization will export the Spark user interface to another server, which is here. Let me see if I can open up. So this server is it's called a local channel. It's a real local channel. It's trying to channel out all the export information to the channel on this website. And this is a hack. It's not provided by Spark by default, but you needed to use a package called local channel to do the port forwarding, so that you can directly have access to the web server hosted by Spark UI. And what it shows here, it's a user interface for managing all the Spark tasks. So basically, Spark is managing all the jobs you have, and it's a schedule module. As you can see here, the first in, first out. the total uptime is just 1 minute because we just spin it up. We just spin it up, and then it has an even timer for all the things, how long it's taking to execute any things. It's a very nice user interface for you to keep track of all your jobs here. If you click the job, we just execute it, which is just parallel execution of to detect if a point is inside or outside the circle. And you can take a look at the information for the task, and you can click all the other information. So what it does is to show you, this is a parallelization function. I'm creating this Python RDD. I'll talk about that in a second. And there are 2 completed tasks here, and you have a lot more information here. You can show some additional metrics if you want. You can take a look at the time taken to run your task. It's in, I believe, millisecond here. So we give you a very, very nice overview about your job, what's ever going on. Just imagine, this is one simple example. Assuming you have 1 million jobs. So all the information about your jobs could be showing up here. You can take a look at those. You can go out to check out the storage available and other things, which might not be, there are some other environment information for the Spark session, and you can check them out yourself. For example, system property, we are running on Google Cloud. So this is trying to show us what this environment is on the Google Cloud virtual machine. And there are a bit more information you can explore here. So these are some executors, because we're not using any storage memory not much storage memory, very small memory here used. And there are many other things you can explore. So with that, let's take a short break for about 5 minutes, and feel free to ask me questions if you have any. And I'll go back, let me know which slide you're, I do have a slide number at the bottom, right? You can take a look at it. Oh, I'm sorry, let me share the slides here. Just 1 second. Okay, let's get back. I'm sorry for a short break, but we have several more slides, much more slides than I expected this time to go through, and the first part took me a bit of time. So I think it's good for us to just go to this Google Library, and let's look at this very simple example to see how all the things are working. Again, I'll just run all, and you can just run this one by one. It's fine. I just want to show you all how all these things working. Oh, it seems busy because I have multiple sessions here. If I'm a pro user, if I'm willing to pay some fees, it will just I can do more than just 1 sessions. So let me see if I can reconnect. Okay, it's trying to reconnect, and then I can run it. So because every session I mentioned, it's a brand new. It's just like a new application running, and you don't have any additional session done for that. So what it does is it's trying to install double check my video audio is okay. My audio is here. So it's trying to install PySpark 1 more time to make sure everything's ready. And then the first, line here is trying to get the Spark session imported from PySpark SQL module. And it's create a session named collab. You can call it different things. And it's configured trying to use the spark.ui port, which is a default port 4050, to export the web interface. That's one we just look at. We'll check that out again 1 more time. And then this will show you, give you the context, which is a context called a Spark. We just save it on the Spark, which will be used as the more or less like a container, contains everything, like a folder containing everything you have, or just like people call it context or a handle to get access to your particular Spark session. In this Spark session, you can create a job doing other things. So that's how you get started with the Spark. The create a session is the first thing to do. And then if you just type Spark or print out some information about Spark, the version and the master and app name, it's just a local Spark session. And next, after Spark session is created, we can just leave it there. So hey, now we created this skeleton, and let's do something else ourselves. Then we link our old code to the Spark session. So this part, it's cell 4 here, shows the sorry, for some reason I have, okay. Shows the part I showed you all on the slides. Basically, we define a number of samples here. It's 10,000, which is not that big. You can try to make this even bigger. And then we try to decide if it's a point random generated, if it's inside 1 here. If it's inside 1, then it's inside. Then I count it. At a later step, I'll count how many points are there inside, and then I divide that by total number of samples I have, and then I calculate my pi. With 10,000 points, I get to 3.166, which is not that bad. It's not so far from 3.14, but again, if you increase number of points samples, you should get better results. So here I will not go into that. You can try it yourself. And then you can stop this session with sc.stop, but in most cases you don't have to, because whenever you leave your current window or you get away from your current session, it automatically closed. But it's a good practice to have sc.stop be part of your code, so that it's just like writing your parentheses. You always have the left and right ones. You're always guaranteed to have something conveniently stopped and wrapped up. So it's a good practice to keep the sc.stop there. And what else? So this is a trick I found online when people are trying to use a local tunnel, which is a JavaScript packet, which can create a tunnel and through another online service, which is provided for free. And I believe it's somewhere in Italy. I forgot where it is. But when you click it, it'll point you to a server, and the server will be tunneling through your Google Cloud server, and it linked to the port exported by the Spark UI, and give you some access to all this information. I already showed you all here. You can explore this when you have time, but it's a very, very nice user interface for you to keep track of all the jobs and even look at the performance for different tasks yourself. Okay, so that's the very first example for Spark on Google Cloud. And even though we are not directly using any resources, but we are using cloud computing already, because Google Cloud, it's a cloud computing resources. It's just, you are doing all the calculation remotely. You are not running PySpark on your local computer. And here I'm running on my iPad, and I don't have PySpark installed on my iPad, but I still run it on this Google Cloud Computing system. And this web browser, Google Chrome, provides this interface for me to interact with my application. So that's one of the ways that cloud computing is working for us, which is, most of cloud computing applications are using web browser as the front, as the management session is created for users to do things on the cloud computing systems. And we probably will be seeing more and more of those. JavaScript is making all the interactiveness possible. As you check out, as you probably see in the UI, the Spark UI, it's based on JavaScript, and it's creating some very nice interactive plotting tools for you, and it's getting there. It's getting more and more user friendly, and it's much easier to use nowadays compared to several years ago. So in part 3, we'll introduce some basics of PySpark, and RDD and DataFrame are the two most important concepts in PySpark that we'll get into details. And this is the same Spark session I created previously. It's just like written in a different format. It's the same thing you saw in the Google Cloud notebook. And we start by installing PySpark, and then we import the Spark session. And then we create this Spark session by calling various functions, giving the name. all these are just configurations. Whatever we do app name here, clamp is just, we give it a name and we provide the network port and also the port number and create it through this interface. So what we are doing here, we are creating the session here. I mean, the session is, but the session doesn't really do anything. It's just open up the more or less like a pointer for us to point into the particular session to kickstart some jobs and tasks in the future. But internally, we needed to create some data structure. This data structure will be containing all the information we want our Spark to handle. And we want this data structure to contain the applications we want Spark to run and to submit, to schedule, to manage, and to all other things. And resilient distributed datasets, RDDs, is one item, or you can consider it as one data structure to hold multiple set of data items distributed over a class of machines. So it manages all the data across multiple systems. Even inside one node, it has a data system across distributed files. Probably in different directories, and you can use RDD to manage all those. So resilient basically means it's fault tolerant. Whenever something wrong happens, it has a built-in mechanism and algorithm to recompute the missing and damaged partitions. Of course, there's always a limit. If, for example, we have a redundancy for a certain number, say, just for example, 5, probably means if you have up to 5 files missing, you can reconstruct it. If you have more than that, there's no way you can do this. It's the same, the same idea. It's built into disk arrays. We are building up, managing all the storage system. A similar idea is built into parity checks for you to check if there are any errors. If there are any errors, you can rebuild the data based on the data you have. So the reason it's doable because you have some extra redundancy. The data you have, you might have multiple copies, or you have copies created just based on some compressed information, and you can reconstruct the data if it's missing. So that's the whole point behind this resilient capability here for RDD datasets. Distributed means it's distributed. All the data are on multiple nodes, probably on even different clusters, because if you are using Meso or others to manage multiple clusters and multiple nodes, there might be one of the data might be sitting in US, another one might be sitting somewhere in Europe. So it totally depends on how you define and analyze and allocate your resources. And the RDD can handle data differently. So here's the last one. Dataset just referred to the data to work with. So that's the data you collecting. So Spark will take your dataset, will transform and convert your data into RDD format. It will create some extra copies or redundant information based on the data you provide, and then distribute your data across multiple nodes it's managing. So just consider it's a file management toolkit for you to deal with different files, and that's one of the most important features for Spark to help you manage data in a resilient and distributed manner. To create RDDs, it's very straightforward. You start by creating a Spark context. The context is an attribute of a Spark session. So a Spark session is considered more or less like a process. When you start a code or start an application, open up some application, open up a web browser, you create a new process. You can consider Spark sessions like a process. Inside this process, you can have multiple contexts, and then we are creating one of the attributes of the Spark session. And then you can create a RDD with a list. You can create a parallelize 1, 2, 3. So this will take this list as the input, and it will create a distributed resilient dataset based on these 3 numbers. How it is doing that internally, that's not something we need to worry about. So this is a way how it's handled internally, taking 3 numbers, and it will do some shuffling and do some manipulation and create some redundant information, and then distribute it across multiple nodes it's managing. At least this Spark session is managing. You can do the same for text files. If you have a very big text file, you can use a SC text file to take the input from this information, this text file. Could be millions of characters or words. This will do the same thing. It will create some redundant information and then cut that into small pieces and distribute it across multiple nodes. So you can do simple mapping, very similar to the mapping you're doing with the Python. You can create a, don't worry too much about this lambda function if you are not familiar with, just consider it's a function. What it does is just do the negative of that value. X, you can consider lambda x here is like fx equals to f minus x. Basically just give you the negative value of the whichever value you input. So this mapping basically is just trying to do the negative value of whatever value you're inputting. Of course, this value should be an integer or real number, right? So this is a minus function. You can do the mapping here. In the same way, you can do the filtering, which is this lambda function, which is an anonymous function. It's trying to do the module 2. Whenever this one is an even number, you'll get true return. Otherwise, it will be false. So it's trying to compare if this could be evenly divided, could it be divided by 2 cleanly. So it's trying to detect if this is an even number. So that's a minus filter. And then finally, you have this flat map. It's trying to map each element to 0 or more others, and it's just give you a mapping from one number to a range of numbers. And it's another way of mapping all the functions. But it's not commonly used unless in some special cases you probably want to do this flat map. But it's some very nice utility when you need it. So all these are just taking the existing list and trying to consider it's already created. You already have this nums as a RDD dataset. So you can do the mapping, filtering, and other all kind of manipulation with RDD. You'll be returned. Another RDD will be returned. So you can keep track of all the changes, etc. So all this return RDD, as it will be working just the same as the previous one. It will be distributed, and it will provide some redundancy as well. So all the work will be done, transparent to users. You don't need to know the details how things are working, but you just know that this is the object I'm dealing with. As long as you know what they are, that's sufficient. And how all this will be distributed, will be shuffled, it's not your concern here as far as the Spark is concerned. So Spark is taking care of all the underneath distribution and shuffling for you. So here comes some basic actions for RDD. You can do a local connection. Consider you have a num created with all these 3 lists. When you can get a local connection of all the numbers, you get 1, 2, 3. And then you can take arbitrary 2 element. It will give you 2, and then you do the counting and do all the other operations based on this data you're creating. Okay. So Spark dataset, it's the way how it's working and how it's distributed, it's completely how can I say, it's a computer science operation. But, since you don't need to worry about the splitting and other distribution and redundancy creation, all you need to worry about how to use the data. Actually, the way how the data is represented, it's showing to a user, it's just like a data frame. And if you're not familiar with data frame, it's some concept defined in pandas. And pandas are probably not defined. First defined, probably used in R first, I believe. And then pandas adopted the idea of data frame and trying to manipulate purely based on data frame. That's what the pandas is mostly good at. And data frame for users is just like a tabular data, just like a table, like Excel file. You open it up on your Excel or Google Sheet, and you can see you have columns and rows, etc. So data frame is just like that. But internally, how it is stored, how it's manipulated, it's not our concern. We are concerned how the data could be represented to us for us to analyze it. So if you are familiar with the Pandas data frame, the Spark data frame will be just in the exact same form. A lot of functionalities that can directly usable, directly applicable for Pandas data frames, they can directly be used in Spark. In a sense, the same function names will be used, the same argument list. Of course, implemented differently. All the Spark data sets, data frames are implemented in Scala, as we mentioned previously. But the way it's written, it's very, very similar to the way how Pandas is handling data frames. So that's making it easy for users, especially Pandas users, to switch to Spark data frame. So data frame could be constructed from a wide array of sources. Could be structured data files, CSV files, like comma separated variables. You can also directly use the tables from Hive, which is another storage service. Don't worry too much about it. If you don't know about it, it's fine. Basically, so the take-home message is that data frame here in Spark can take a big chunk of a wide variety of formats, as long as it's structured. And data frame can take it, can reformat it into data frame it can recognize, and then you can use that to convert that into RDD, or you can even read from existing RDD and convert them to data frame. So, for user data frame, it's not more than just tabular data set, just like what you can see on the spreadsheet. And you have columns and rows, and all the functionalities in dealing with data frame in both Spark and Pandas are to make it possible for you to create, update, what's the name? I'm sorry, create, read, update, and delete all those entries inside this data frame. That's called a CRUD, C-R-U-D. That's how I remember it. It's called a CRUD principle. Whenever you have any object, no matter it's Python, Java, Scala, C++, you need to define at least 4 operations. These are minimal operations you need to define to deal with those objects. CRUD basically create, read, update, and delete. Okay, so that's pretty easy. All the objects like a data frame, no matter what kind of functionality you have, no matter if it's a Spark or Pandas, they should have all these functionality for you to deal with those. And another tricky thing is for Pandas and Spark is that they needed to provide some functionality for you to easily and quickly locate a certain element. And that's the query part. That's the SQL part. And Pandas has such searching functionalities. If you do a data frame and with some criteria like A, greater than 10, etc. So you can filter out all the rows and columns with the columns A. You can filter out all the rows when the column A is greater than 10, or it's less than 10, and then you can create a tables based on that. So, in addition to CRUD, you need to provide a query and all other quick searching mechanism. So here, this is a very simple code piece to create a data frame, and we start by reading a file, a CSV file, and this is a local file, and we'll show you in the Google Cloud. I'll show you how to read it from online file, and we can directly download the URL file. You can get the URL and download the file and read it from Spark files. So it's trying to use some built-in schema, trying to detect the numbers automatically, because for all the files, especially CSV files, they are separated with the commas, and each column they have a similar data structure. So the reader, the Spark files, can directly infer the data type of the certain columns. For example, if it's numbers or integers or double precision floating points or strings or some other objects. So this function, Spark files can directly infer. So that's why the last argument here, I'm just saying, infer schema. Schema here basically more or less like the type of data or the size, etc. All the schema you use to define your database. So here it says infer schema equals true. That means I want to use the built-in mechanism of Spark files to help me to automatically detect all data type. it's pretty useful, but in some cases you might see some errors, but you can always fix the schema. And I'll show you how that works in the example. So here I created a simple list of an automobiles, with different brand, different numbers, and you can create that. You can create a data frame from a list. And again, you can do the same thing with a dictionary, and there are some other examples. So it's pretty straightforward to create, data frames in Spark. Now, remember this. Now, after you create data frame, you can save that into RDD, and then you can share it with other people. Other people can take it, they can process it, and you can analyze using the cloud computing resources. And you can easily do this yourself. So to operate on the data frame, it's very, very similar to Pandas data frame. And the syntax is almost identical. And for you to pick a certain column, it's just use a data frame, a square parentheses, and put the column name there. Okay. Or if you're familiar with Excel, you can use this like a fancy way to manipulate with Excel files using programming interface. And all we are doing, it's kind of similar to what you're doing with Excel in general. It's just like using command line interface or with a script. We are dealing with the tabular dataset, as you can see in Excel or Google Sheets. But these are trying to provide, for the first one, it's very simple. We select the column name. We show the first 5 rows of it. The second one is trying to select all the select the names and also select the mileage per hour. But the mileage per hour, I add X to 100 to it. And then I show first 5 column to it. Okay, so if I'm not familiar with the Python method here, so every time here, df itself is a class. It's an instance, which is an instance of a class. This class contains certain methods, like select is a method of the df data frame class. And this method will do all this. It will output everything, and the output will be another data frame, and it has a show function for that data frame. So you can chain up all the functions one by one with the dot operations. So that's usually it's pretty common technique in Python programming when you are using classes and objects like that. And for those of you who are familiar with R and probably some other language, might not be, might feel this kind of weird kind of syntax, but it's pretty straightforward after you get familiar with the basics of the Python programming language. So next we'll move to Spark SQL. And if you're familiar with SQL, this is just straightforward one. You just construct your query and just use Spark function to call it, and that's it. Because SQL itself is standard, international standard, and everyone is using the same SQL language to do the same thing. It's just the way how the SQL is implemented, is parsed, is executed are different for different databases. But the SQL itself is a standard. So if you are not familiar with SQL, you probably want to learn it. But if you're familiar with it, nothing more, nothing less. It's just like the traditional one. It's just how you run those SQLs, send those SQLs to Spark sessions, and Spark context will be different. So first this is running a SQL. It's trying to create a temporary view for this data set. The reason we want to do that because we don't want to accidentally modify the data set. So the view is more or less like a temporary copy of a data set just for query and other information. So that's a good practice to use a temporary view for that instead of directly operating on the data. So the way how you do SQL query is to construct a SQL query, like the select star from auto. This is a standard SQL language. You select everything from this table. And then you save that into this data frame. Because when you select that, after this select star from auto is executed as a SQL language with a Spark framework, it will return a data frame. This data frame will contain the table, most like when you submit, when you more or less like when you're getting a subset of your table set. Even though here it's a select everything, but you can select something from it. So you always get a subset or equal to the original table. The table itself is nothing more than data frame. So the next statement here is just trying to show 5, the show first top 5. as we talked previously, you can simply put a .show5, after the SQL function, you can get the same thing. You can just, I'm sorry. So we all save this into SQL DF. We all save them into files. So definitely we don't want to put a .show5 in the statement previously. But if you just want to show top 5 without saving the data, you can directly put a .show5, in a previous statement. So we can create a global temporary view. We can do something similar here, and we can so query here is mostly about finding the information you need and then save it to a data frame, and then you can manipulate with it. And running all the queries, it's just like constructing that into a string and just use a Spark SQL to run it, and then you save that output, and then you can deal with data you queried. So Spark Streaming is a streaming facility for you to deal with streaming data, just like live audio stream. A video stream from YouTube. That's a streaming information. And Spark can take care of this streaming processing and in real time, depending on how fast your processing application is. If it's really, really fast, you probably have a less latency. If it's taking a long while, then when you're streaming data out, then there'll be some delays. In the same way, when you have people doing the live, broadcasting of YouTube, there are always some delays because there will be some processing in between, right? And then if you see multiple streams from different sources, they have some latency. So Spark Streaming is taking the input in data streaming, could be sensor data from IoT, Internet of Things, could be video, audio streaming, and all other things. So internally, it will be saved as a sequence of RDDs because all the data streaming, no matter what, you needed to have a cutoff. For every time you get probably 10 milliseconds data coming, you stop it, you process this 10 millisecond first, and then you go to the next 10 millisecond. So you can also, depending on how much latency you want to apply, you can probably wait until 10 seconds, then process the 10 seconds of data, and then do the streaming. So it's depending on your application, depending on the requirements for real-time, capabilities of your application. So you can save that sequence at different intervals. And also machine learning pipeline with PySpark, it's actually very straightforward, depending on what you want to do. But PySpark itself provides some machine learning libraries which can do simple classification, regression, decision trees, random forest, clustering, all the other things that commonly can easily done with scikit-learn and some other packages. And I believe it has multiple packages doing all the regression and probably some others. So the machine learning library workflow utilities include some feature transformation and pipeline construction, etc. So it has some hyperparameter tuning to improve the performance of your machine learning models and also help you to evaluate your models with some metrics here and there. So we'll have one example to show you a very simple linear regression, even though it's simple, but it contains basic skeleton about how you get started with other machine learning models. Since this, online course is not about machine learning, so we'll not go into the details, but it's just trying to show you how this pipeline could be created with PySpark. So to deploy on a cluster of your Spark, it's currently supporting multiple cluster managers, as I already shown that in the diagram in the first part. And you can start with a standalone simple cluster manager. You just, all the nodes are yourself. It's like on-premise setup. You manage your cluster. You have a logging node, which will be working as a cluster manager. And then you have some other nodes connecting to the manager. And whenever you submit something to the cluster manager, it will send your job to your nodes, individually, depending on the availability of the computing cores, or you can check the load of each node. If the node is already working, if this particular node is already working on some other things, you probably want to, assign a job to another node, etc. It's just scheduling. That's standalone cluster. When when I was a graduate student, I managed a small cluster for my group. It's quite a lot of work. And back then, there was not many software toolkit can help you to do all this yourself. Get everything started quickly. You have to do all the installation manually. A lot of manual work, but it was quite a learning process for me. Another one is Apache Mesos. It's a pretty general cluster manager that can run Hadoop, MapReduce, and many other applications. It's really, really big. I had a student work on this previously on a different project. It took him a while. It's pretty messy. And sometimes if you get some errors, it's pretty hard to debug, to figure out what's going on there. But once it's working, it's really, really powerful. It can do a lot of things cannot be easily done by other simple cluster managing software. It can help you to connect multiple clusters and help you run Hadoop, MapReduce, and help you to run Spark, and all the things combined. You can schedule your jobs in a very, very flexible way. And that's Mesos. I'm not sure how actively maintained it is, but it once in a while, I think you can see some updates from this community. Hadoop YAR, it's a new resource manager for Hadoop. Back then, Hadoop is using its own resource manager, which was not so efficient. But after Hadoop second version 2 was out, Hadoop YAR was the default manager for Hadoop 2, which is pretty powerful, and you can look into that following the links. And Kubernetes is an open source system for managing and deploying all your containerized applications. So it's worked mostly with containers. When you have different applications already run up in a containerized format, and you can easily download it and run it, deploy it with the Kubernetes. And this is a pretty popular toolkit, but again, depending on your applications, this might be not suitable for your application. But if you are focusing on very specific code or particular program, you don't worry too much about across multiple platforms. This could be probably the tool you want to try out. It gives you a very easy way to manage different clusters that can directly spin up your containers on those clusters. And it's very easy to use. But again, for myself, because I'm not using cluster containers, I usually run containers once in a while, just individually. I don't use Kubernetes myself, but according to some online reviews, it seems to be a very, very powerful tool to manage tons and tons of containers running across a large computing cluster. So next, we'll have two, we'll have two examples to run. First one is how to create data frames and try to use a PySpark SQL query to send the queries to the PySpark framework. And the last example is trying to use a PySpark machine learning library to just do a very simple linear regression to solve a linear regression problem. Let's go to this one first, DataFrame. And just to make life easier, you can, it's hidden here. Let me click the run all. I'm sorry, it seems not connected. Okay, here at the top right here, if you don't see RAM disk with a check mark here, that probably means your session is not connected. You probably want to connect it to click the collect. And then if once it's connected, you can just run all, and it will run all the cells for you automatically. Again, it's into download PySpark, but it's only for Google Chapter. If you set up your own Jupyter Lab or Jupyter Notebook environment, you don't need to do this yourself. And because it's your own system, after it's installed once, it will be stay in your system. But here, every time, the session will be cleaned up and nothing will be left, and you have to reinstall all this every time. So first time we get PySpark installed, and then we try to create a data frame by reading from a CSV, a JSON file. CSV file or JSON file, both. So we are just trying to show how that works. And it will take a while. Okay. So in this example, I define this URL for both the CSV file and JSON file. So we can do them both. And then you can use this add file to directly download it from CSV URL. Previously, it's not working, but now when I check it, it seems you can directly use Spark in the 3.3 at least. I checked to download this file from the URL. And then after the file is downloaded, you can directly read in to your. I'm sorry, there's something wrong here. Let me go back to. You can directly read in. I'm going too far. You can directly read in with Spark file to get auto.csv because the CSV file will be saved. If you click the menu bar to the left here, and you can see there are multiple directories. Where is the Spark warehouse? These should be saved, but it seems to be saved somewhere else, not saved here. I'm just trying to see the file. It's not saved here. Okay, because I didn't save the file. It's just reading, seems to be reading to the memory directly from the auto CSV. And then I'm trying to print out a schema. That schema basically showing what data type I have. Let me close this one. So its schema shows what data type I have. If it could be now, because sometimes you don't have entry, so it could be now for the database. And all these are nowable equals to 2. Basically, those could be empty variables. And the default info schema is doing a pretty good job. MPG was considered as a double, more or less, it's a real number. Cylinders, number of cylinders is an integer. I'm sorry, this is automobile CSV file, contains some miles per hour, the mileage, number of cylinders, and horsepower, weight, acceleration, displacement, and the year, and where they are from, and the name, etc. This contains pretty decent table of automobiles for, I'm not sure how many. We can check how many we have later on. Here we are just showing top 5 rows. And next, we'll use the JSON file just to demonstrate that the same reader could be read from JSON, but instead of read, look at the file here. Instead of using CSV, we are changing that into JSON. This is just 2 different functions implemented in Spark to read files of different format. JSON file is kind of similar like a dictionary in Python. And it can directly read in and give you create this table for you automatically. So this is what we read from the JSON file. It's kind of similar, nothing more about it. And next, we want to correctly cast the type of all those columns to make sure, for example, mileage per hour, we want it to be integer. Of course, it could be, it's not it shouldn't be integer because, we have some. You can probably change that to float point or double type, which shouldn't be integer, and just fix that. And then you can specify whichever type you wanted, and this will not use when you talk about schema, the infer schema, you need to change that setting into false. Otherwise, it will be using the default infer schema. I'm sorry, the schema here you need to specify the user schema here because when you use the infer schema, the schema will be set with the user schema defined by you previously. So now it's not using the default inference for different data types. Now it's using the defined schema you defined previously because if you already know the data type of different columns, you can directly use that. After you do it, as you can see, mileage per hour now turn into integers, which actually is not a good idea. But it's just this one just trying to show you how things are working. You probably want to change that back to double type, so that it's probably better match the data that we have. But anyway, these are examples showing you that you can change the schema of data directly by defining the schema yourself. The same goes for JSON, but you can, you can do the same thing. Now, this one shows how to create a Spark data frame with a list. I create a list with different data types with an integer, string, and since I also define the schema myself. The first one the integer, and then the second one the integer. The third one is string type, and I use my correct data frame to do it because I didn't specify the column name. So by default, Spark will create the column name for me by default _1, _2, _3. So that's the default column names for my integer. But I can specify column names myself. For the field. But so a dictionary, as I mentioned, it's just like a JSON file. You can use this to create auto list as well, the same way. And you can select a certain type. Like here, I'm just select the name column, and I just show the first 5 rows of my column. I do the same, but here, as I mentioned, I already showed this example in the slide. You can add whatever numbers, you can multiply it. You can do some manipulation numerically with your columns, and it will be applied to every element in your column. And it will do the same here. For example, the mileage per hour, you add miles per hour, you're adding 100 to it, right? It doesn't make sense, but it just show you how it works. You can do some filtering here. That's how you do the filtering, more or less like a query without SQL. When I do the filter, I want my miles per hour, this value to be greater than 30, and I show the top 5, and that's how it works. And then I can do the queries programmatically using SQL query, and I select everything from my auto table. Okay, and then or I can just select some other. You can put some other queries. I think there's something res converting. Okay, it's just couldn't find this file for some reason. JSON, auto JSON, probably lowercase auto or capital case. So this could be easily fixed. You can look into that, but that's not a big concern. You can try that yourself as an exercise. Okay, so that's the data frame and SQL query. And next one, I want to show you all this very simple. Again, I need to connect it first because I just closed the previous one. This one might not be connected. Now it's just connected. I can next run my Jupyter notebook here, run my Google Library notebook here. Again, it's kind of, because it's not your machine, right? You don't have full control of all the stuffers packages. Every time we give you a clean installation, it will try to install the package for you. And what try to do here is, for the first 2 parts, it's doing the same thing, exactly the same thing. It's trying to read CSV file, JSON file from the data frame, just create a data frame for us. And it will take a while to run. And then, this is a very simple example. I tried to create a linear regression model with a machine learning library. For those of you who are familiar with machine learning model training and all other things, you needed to understand that we needed to, for the regression model and also for the supervised learning model, we needed to split our data into training and testing, right? So usually it's a rule of thumb to set at least 70% as training data set, and the rest of 30% are testing data set. The reason you want to do that because you want to check if your model is good or not. And if you use all your data for training, right? It's just like, and you will not have data for testing. And if you want to use 100% for training and use some of the data from the training data for testing, it's more or less like someone give you some problem for you to practice and then use the same problem for you to test for a test. And you can definitely work, get pretty high score because you worked out all those problems already for your training purpose. And the reason we want to split it so that your model, whenever you train it, it's only trained on the training data sets. And the testing data sets are not, you have no idea. The model has nothing to do with the testing data set, has no idea about what testing data set look like. So it will give you some good estimation about how good your model is. So what it does here is try to create a vector assembler based on 2 input columns, which are very important here. One of them is weight, another one is mileage. That's are the 2 columns I'm interested in. I'm just doing a linear regression, and I don't do a multilinear. And I represent them as a features. So these 2 columns will be singled out, and a new features column will be created. And to for each, if you print it out, I think it's not running. Okay, the feature column will be created, and if I can run, let's see, type code. I mean, it's not here. See if I can run something. Okay, I created a new feature column, and I'm sorry, it's already splitted. Don't worry about my error here. You shouldn't have the SM error. So the feature column will be containing 2 rows, 2 columns. One is weight, another is MPG, miles per hour. What it does is trying to best fit this miles per hour like mileage against the weight of your vehicle. And you can expect, that's what I expect. The weight and the mileage of the car has some linear correlation. It's a high, the heavier your car is, the more the negative. I'm sorry. There's a negative correlation. The heavier your car is, the less mileage you might have. But this model might be not creating the good results here. I think there's something wrong with the model. And actually, I believe when I was creating this, I did that on purpose. I was asking my students who attended this workshop to figure out what's going on there and what's wrong. But since we don't have time today, so I'll leave this as one example for you all to look into. So there's nothing wrong about this running this model. It's just there is something wrong about which features you want to pick and which one you want to use to do the best fitting, etc. So nothing wrong about the other parts. But again, this is a very simple pipeline you can build. When I said pipeline, all these are working as a single script. You can connect your functions, after functions, model training, pre-processing all together under function. You can build up your pipeline based on that. And that's what I'm saying about pipeline using MLlib. Okay, with that said, I think that's all for today. And I also have 2 slides about some cheat sheets. And I use all these cheat sheets a lot myself because sometimes I just give you a quick reference to all those commands and also functions and all the classes. And it's very, very easy for me to just look up if I need something to when I was working on PySpark and even some other Python-based projects. So I'm sorry, and I think that's all for today. If you have any questions, feel free to ask questions. Oh, actually, I have another meeting coming up at 3. And I'll leave my email to everyone. And feel free to reach out to me if you have any questions. I'll be happy to answer your questions. Throughout the summer, I'll be around. Just feel free to ask me. And I'll be happy to get back to you if you have any questions. And I hope the materials today are helpful. And I hope you all learned something about cloud computing and PySpark. Okay. All right. Thank you so much.
Thank you, Dr. Tao, and thank you everyone for participating. Like I previously mentioned, today does conclude our biomedical data science session. If you look in the next couple weeks or the next coming weeks, we should have all remaining recordings up on the TAMIDS website. So if you want to periodically check that, everything should be posted. Once again, thank you all for joining us for the session.